present you in the name of my colleagues next topic, our paper. This is comparative analysis of 3 different installations. First installation is first and second installation working with CO2, and third installation working with 404A. So let's begin. Main goal is to find electric energy consumption. Why this analysis? Why are we doing all this? First reason is global warming. Global warming because this is the popular topic. The old refrigerants being replaced by the new. Problem is the GWP 404A with 3922. Solution is the natural refrigerants. As a potential substitution, we used CO2. Second reason is energy efficiency. For energy efficiency, we look for electric energy consumption. Of course, there is improvement of refrigeration systems, and of course, when we have all of these 3 reasons, we can approach to the systematic conclusion. Okay, there's, as you see, 3 different refrigeration systems. First one is Cascade 134A CO2. This is an existing installation in our laboratory of thermal science department. Second installation is single stage 404A. And third installation is 2-stage transcritical CO2. What is our goals? Our goals are direct impact on the environment through GWP. Second, indirect impact on the environment through electric energy consumption. And third is cost analysis. Conditions. We must, before we start calculation, we define our conditions. Condensation temperature defined through by the ambient temperature for Belgrade 2017. You can see on the you can see on the diagram below, purple columns are average monthly temperatures for 2017. Diagram on the right is the relation of some temperature, which is calculated. This is the outside condition. Inside conditions are constant. We calculated for evaporation temperature of minus 30 degrees and cooling capacity about 6 kilowatts. First installation is existing installation cascade system of 134A and CO2. On the left, you can see schematic simplified diagram, and on the right you can see thermodynamic cycle. Low temperature cycle is working with CO2, and a high temperature cycle working with 134A. On the next slide, you can see our 3D model developed in SolidWorks. Because it's existing installation, we use exact dimensions and parameters. And it looks like it for real like this. As I said, we need to determine compressor power, because the compressors are the main consume in our installation. So we need to define our power compressor. Its relation from condensation temperature. First compressor is Bitzer compressor, semi-hermetic, and it's constant because he doesn't rely on condensation temperature. Second are parallel Senio scroll compressors, and you can see relation here. Our second installation is single stage 404A installation. As you see, it's a really simple installation, so I will pass on. From the software values, we get on the left this diagram, but because it's the deviations for 1 Hertz frequency step, then we implement our numerical method. So we get better relation. Two-stage transcritical CO2 system. We have 2 compressors and 1 refrigerant, CO2. Because of the low critical point, CO2 goes in a transcritical area. So instead of condenser, we have gas cooler. For that, we need to define our optimal pressure. On the left, you can see gas cooler heat exchange. You can see also that temperature of CO2 is no more constant. So we need to define optimal pressure. Optimal pressure is defined for maximum COP of installation and temperature of air on inlet on gas cooler. For every temperature, we get a line of optimal pressures. That line we, with correlation, show here. And you can see also relation of compressor power from condensation temperature. On low temperature compressor is constant, but high pressure compressor it's changing with condensation temperature. And here are our results. As you see, it's quite the same for the single stage 404A and cascade 134 CO2 installation for electric energy consumption. Transcritical is worse installation. It needs big amount of electric energy to start the compressors. As a conclusion, we look 3 points. Global warming. From the point of global warming, CO2 is a good substitution for 404A. Also, combined with the 134A, it's also good substitution because this is the medium GWP. Second our goal, it was indirect impact on the environment through electric energy consumption. So, cascade is good substitution, but transcritical two-stage CO2 is not. Of course, it's. I need to mention that we calculated only for small installations, small capacity installations. So, if you want to take these results, you must develop another analysis. And of course, cost analysis, when we look only investment. Investment, one stage 404A is a little bit cheaper than 134A CO2 cascade. So this cascade can be good substitution for this system. Also, besides, transcritical two-stage is not. Before I finish this presentation, I want to show you something. That this presentation was not only about this analysis, but for this cascade 134A and CO2. It's all about, because this is existing installation in our laboratory, we have some others in the past 3 years which we developed. Before, it looked like this. This is our old laboratory. It's a little bit of mess. It's full of old and unfunctional equipment. So we clean it up. There was tons and tons of equipment. Then we start developing, with the help of companies, our installations. With the help, and this time I thank Soko Engineering and DAFOS for this, they commissioning the cascade system on the picture. We also have a single stage 407C Emerson installation and heat pump with a propane 2 and 20. Of course, I want to thank Emerson and MPG for this. Thank you for attention.